Okay, so again we begin a new lecture. This is lecture 36 of phase equilibria course. So let me just give you a brief recap of previous lecture. So in the previous lecture we looked at for instance drawing the vertical sections. So we looked at the better ways to define the ternary phase diagram. So we looked at what is a liquidus plot. Liquidus plots are basically isothermal contours of the liquidus surface found on the liquidus surface, which are projected in 2D. So they are plots like these. So for example, for isomorphous system you may have situations like these. So these are various temperature profile T1 to let us say Tn as you go from ABC, and they basically determine the liquidus surface of the ternary phase diagram. Then similarly you can have solidus plots as well. Then we looked at isothermal sections. So isothermal sections are nothing but sections drawn at constant temperature, unlike the previous one. So you can have for instance the phase fields. So if you go to binary, if you see ternary isomorphous system at high temperatures you might have liquid. Whereas somewhere in between you will have liquid plus solid, then solid. So something like that. So this is at a constant temperature. Okay, so this is liquid plus solid region. And then we also looked at isothermal isoplates, and these isoplates are nothing but vertical sections. So basically they are drawn vertically parallel to temperature axis and intersecting two parts of the phase diagrams on the horizontal plane. So essentially they can go from so if they go from A to B, then it's nothing but a binary phase diagram from A to B. But what you want to do here is, for example, you want to go from pure A to let us say so let me just draw isoplate. So essentially these A, B, C, AC, AB and BC are nothing but isoplates, but they are vertical, they are binary phase diagrams. Here you want to go, for example, you want to draw this section, vertical section. Okay, so this is isoplate. You may want to draw another one, which is let us say like this. So these are the isoplates which give you evolution of phases as a function of temperature for given ratio. So you can see that this has certain A by B ratio, this has certain B by C ratio. So you are moving from certain A by to certain B by C, and in between, for example, you will encounter certain specific compositions, and these basically give you evolution of phases as a function of temperature along this line. So along this line of composition you see the phase evolution as a function of temperature. So these are nothing but isoplates. All right. So in this lecture what we will do is that in this lecture we will look at some ternary phase diagrams of specific types. So for example, we begin with systems that have two phases. By the way, another thing which I'll come back to this little later, another thing that I skipped is application of phase rule. So we know that F plus P is equal to C plus 2, and when pressure is constant, then this becomes F plus P is equal to C plus 1, where F is the number of degrees of freedom, P is the number of phases, and C is the number of components. So you can have various situations in the ternary phase diagram. So for example, you can have situations where you have a single phase equilibrium. That is very rare, but you can see in ternary isomorphous systems it may occur. So, if you have situation like this, then C is equal to 3 and P is equal to 1. As a result, F is equal to 3. So, you have 3 degrees of freedom here basically. There are 3 independent 3 degrees of freedom or 3 independent variables. So, what variables could it be? So, you have the variables are F, A, so you can say C1 and C2, because if you have 3 components 1, 2, 3, you know that x1 plus x2 plus x3 is equal to 1. So, if you define 2, the third one is automatically known. So, the 3 variables that you have available are composition of one component, composition of second component and the temperature. These are 3 variables that you have, which you can vary independently in a single phase field. So, if you have for example, a situation like this, let us say this is isothermal section of ABC in alpha phase region. So, you can vary so you can, whether you are at this point, whether you are at that point or this point, it does not matter, you are always in single phase regime. So, this is like changing the composition. So, if you go to different temperature as well, then also if it is alpha phase field, and you can vary temperature as well as composition simultaneously, and you will still have single phase field. So, it is like going from one point to another point in 3D and still going from alpha to alpha, all right. So, this is single phase equilibrium in a ternary region. You can have 2 phase equilibrium. If you compare this to binary, by the way, in case of binary you will have for a single phase equilibrium you will have 2 variables, that is temperature and composition, and that composition is basically percentage of one component and second one is automatically known. Now, if you compare, if you now go to 2 phase equilibrium, which is possible for example in ternary eutectics or even in case of isomorphous where you have liquid plus solid regime. So, you have F is equal to C plus 1 minus P. So, C is 3 plus 1 minus 2. So, you have 2 degrees of freedom. So, what are the 2 variables you have? 2 variables that you may have is, one is temperature and second is composition of one component, but a better one would be you fix the temperature of one component. Okay. Temperature is fixed and you vary the composition x1 and x2. So, you vary 2 compositions x1, x2, but you remain in isothermal plane. So, this is 2 phase equilibrium. Similarly, in case of 3 phase equilibrium, F is equal to C plus 1 minus P, and this will be 3 plus 1 minus 3, 1. So, you have only one variable, one independent variable, and that could be either temperature or x1, that is it. Mostly it is temperature that we talk about. And then you have 4 phase equilibrium, which is not present in binary systems. So, if you recall that in case of binary system, if you have 2 phase equilibrium, then your degree of freedom is 1. So, if you move temperature, composition is automatically fixed, or if you change composition, temperature is automatically fixed. Similarly, in 3 phase equilibrium, whereas in binary system it is invariant, which means you have no degree of freedom, which is like a point in a binary phase diagram. In this case it is a line. So, you can see that there is 1 degree of freedom. So, in this case this is, you can say, a 3-dimensional change, this is a 2-dimensional change, you can move along a surface, this is a 1-dimensional change, and in the 4 phase equilibrium you have F being equal to 0, which means it is invariant. and this could be situation like ternary eutectic. So, we saw for example, somewhere here you have ternary eutectic in isopleth. So, this is the isopleth you have. So, at this point liquid and alpha plus beta plus gamma, they coexist. So, this is a 4-phase equilibrium which is not found in binary systems, but in ternary systems. So, as a result you have you can say example is ternary eutectic. So, these are the 4 possible scenarios that you will encounter in case of ternary systems as far as application of phase rule is concerned. Alright, so now let us get moving to some ternary examples, systems examples, and we will first start with ternary system with 2 phases. By the way, one thing which I forgot to mention, there are 2 books you can refer to. So, let me just write it in the beginning of the lecture. So, the books for ternary phase diagram understanding could be, the first book is ternary phase diagrams in material science by D.R.F. West and N. Saunders. It is a very nice book, comprehensive book. And the second book that you may consider, which has only a chapter on phase ternary phase diagram, which is phase diagrams understanding the basics. This is edited by F.C. Campbell, and this is from ASM International, and this is from Institute of Metals, UK. Institute of Metals, I think it's UK, yeah, and it's basically you can say Mane, M-A-N-E, by Mane Publications. So, these are the 2 books that you can refer to while reading about ternary phase diagrams. What I am teaching in these lectures is mainly adapted from those 2 books. So, let us begin with the ternary system that contains 2 phases, and this 2 phases basically, so you have 3 components. A, B and C. Okay. The condition is they are completely soluble in each other in both liquid as well as solid states. So, so you will have one liquidus surface, basically curved surface, and you will have one solidus surface which is again curved. So, let us see how do we draw this. It is a little complicated, so bear with me if I do not do a very good job at drawing it. Okay, so we start from, let us say, A, B, and then we draw the vertical lines here. These are the vertical lines, right, and let us say we have a situation like this. So, this is the liquidus, let us say, this is the liquidus surface, and the solidus surface would be, let us say, this is the solidus, and this is for the back side. So, this is A, B and C. So, this is how the phase diagram will look like. So, you have liquidus, this is solidus. So, phase fields will be, you have liquid here, in between these two solidus and liquidus you will have liquid plus solid, and then somewhere in between you will have only, somewhere below the solidus you will have only solid. Now, let us say in this case when you determine the liquidus and solidus, so if you determine liquidus and solidus, so how you do is that you basically by plotting isotherms as I showed you in the last class. So, if you draw these isotherms, they allow you to determine for a given composition what is the start of solidification and what is the end of solidification. So, in some cases what may happen is that this liquidus and solidus may also touch each other at certain point, and this could be a maximum point. For example, you take two surfaces which may touch like this, or it could make a valley where there is a dip somewhere in between. So, there could be a maximum and minimum. Now, the process of solidification, let us say you take a composition X, okay. So, you take a composition, let us say X, all right, and let us say, so you take a composition X which cools from temperature T1 to T4. So, T1 is high temperature and T2 is low temperature. So, the way it goes is that at temperature T1, so if you draw on the side, let us say, so this is what you have. So, on the side of it at T1 you have a composition liquid here, solid is somewhere, let us say this is solid. So, this is L1 S1 at temperature T1. Then as you keep solidifying it, the liquid will slowly convert into solid. So, this is L2 S2, then it will again go, if you go to lower temperatures. So, this is T2, this is T3 and this is T4, all right. So, you have L3, L4, S3, S4, and these four lines can be joined together like this. Similarly, these four lines can be joined together in this fashion. So, when you look at this in the 3D, you start for example, for a point this, and the liquidus let us say move in this fashion on this surface. Correspondingly, you will have some movement of similar movement on the solidus, which can be projected like this, and this is nothing but what I am projecting on the left hand side here. So, this is the liquidus surface. So, this one is the liquidus, the blue one, let us say, which moves its composition, and this is the change in the solid composition as a function of, just like a binary phase diagram we are looking at in ternary, but you cannot visualize this in 3D very easily. So, you need to draw 2D projection. So, this is how the liquidus composition will move, and this is how the solidus composition will move. As we know that when you form liquid will reject solid, as a result there will be change in the composition, and as you keep on forming more and more solid, there will be subsequent changes in the liquid composition as well as solid composition. And as far as it is equilibrium cooling, you allow slow conditions to prevail. As a result, liquid and solid achieve equilibrium composition. So, if you take the projection of these lines on the 2D plane, you will see this is, for example, X. The liquid composition, for instance, may move in this fashion, whereas the solid composition may move in another different fashion. So, this could be the solid. So, this is X, this is, for example, movement of liquid. So, this is L4 prime and this would be S1 prime. So, these are the contours that have been projected on 2D in the basal plane of this prism, and these are the changes in the composition. So, these lines which are from L1, let us say this is X, okay, and these are compositions. Okay. So, these lines which connect L1 to S1 through X. So, this is also X, this is also X, this is also X. So, these points, first of all, L1 and S1, L4 to S4, they are compositions of liquid and solid at various temperatures. Okay. So, at temperature T1 you have liquid L1 plus solid S1 in equilibrium, alloy composition is X, but liquid of composition L1 and solid of composition S1 are in equilibrium. At temperature T2, L2 plus S2, so liquid composition is L2 and solid composition S2. So, as you come down T4, you have L4 plus S4 situation. So, liquid of composition L4 and solid of composition S4. So, the way you determine their, so you apply now the lever rule. So, at any given temperature, if you want to determine the percentage of phases, can be determined by applying lever. So, here for example, if you take a temperature, let us say, so at T3, if you go back to previous number, this is liquid composition is L3, solid composition is S3 and alloy composition is X. Percentage of liquid at L1, okay, at temperature T3 would be X S3 divided by X divided by L3 S3 into 100. Percentage solid will be equal to, at T3 will be equal to X L3 divided by L3 S3. So, the key thing is that these tie lines have to pass through X. However, what you note is that because it is a 3D diagram and these are curved surfaces, these tie lines are not necessarily parallel to each other. They may be in different directions depending upon the way solidification proceeds. So, for example, if I take before I do that, let me just draw the Liquidus plot. For example, Liquidus we have seen, how will it look like? If you draw the Liquidus for such a system, so this is, let us say, A, B and C. The Liquidus may vary something like this. You will have these isothermal contours. So, these are isothermal contours depicting Liquidus. So, this is basically a Liquidus projection. Now, you go to let us say we take solidus, we take a few isothermal sections. So, let us say we take this first isothermal section, which is something like okay. So, this is, let us say, at temperature T2, okay, and then we take another one or I can maybe, so this is at T3, okay, that is better. So let us say this is A, B and C, this is also A, B and C. So in case of T2, let us say the phase fields are something like this, right. So this is liquid, this is solid, and we are here at some point x here, and in this case the tie line is something like this. This is, let us say, L2, this is S2. When you move to T3, which is lower temperature, the solid regime little bit expands, liquid regime shifts to the left. The x point is somewhere here, which is same as, the x will not change, but the direction of this line, so x may remain same, but you can see that this is in this direction, whereas this could be in this direction depending upon the nature of the surface, but this x will always fall on the same, always fall on the tie line. So this will be, let us say, point x2, this is x3, same as x, basically the alloy composition. So essentially these tie lines may not necessarily remain exactly parallel to each other as you cool the alloy. So eventually as you get down to lower temperatures, so as you go down to lower temperature, if you draw the cross section, you will have not very good. So you will have alloy X, which is completely solid. So this would be completely solid at this point. This thing might have moved somewhere here, but does not matter. Your alloy has completely well, you will not have, for this composition, for isomorphous system, you will not have this thing. So you will have complete solidification by this point. So what I wanted to say was basically that you can determine the composition of two phases in equilibrium by using the tie line rule, applying the lever rule. You can determine the phase fractions, and you can visualize the solidification using by drawing the isothermal sections and then looking at how the compositions are changing for the two phases. So if you want to, for example, draw the isothermal section, what you do is that, let us say, if you want to draw, let me choose this point. If I draw the isothermal section, so not isothermal section, but the vertical section, that is isopleth. So if I draw the isopleth will look something like this. So you will have this is liquid, this is solid, this is liquid plus solid. So this is from, let us say, A B, so this is from A B. So it is not from pure A to pure B or pure B to pure C, it is from some composition A which has certain A by C ratio, and this is another composition B which is A by B ratio, and you can see the phase boundaries are not closing. So it is not complete phase diagram, it is just a section, vertical section or isopleth that is taken along that parallel temperature axis. So what we have done in this lecture is we have just looked at some graphical description of a ternary phase diagram consisting of two phases. So A and B and C are completely miscible in both solid and liquid state. We have seen how to draw how one can determine the phase compositions and phase fractions by drawing the tie line, and you can visualize the solidification phase changes by drawing the isothermal sections and drawing isopleths. So in the two other ternary systems, and before we finish this discussion, thank you.